answer what the intersection is?
Sure. Yeah, if you're interested, it's 770 Kelvin and 0.35. So it is. It didn't really match up on the curve that he gave in the test either. It's like 0.5 to here. But yeah, that's the answers. I think as long as you know how to do it, you obviously got to be pretty lenient with graphing since it's all graphical. So part C is by diluting the feed stream with an inert species, it is possible to achieve an adiabatic temperature of 600 Kelvin with the feed maintained at 300 Kelvin. Write down the equations that must be solved to determine the inlet mole fractions of the inert species, so Yi, and that will allow the reactor to achieve a given temperature at equilibrium when all other inlet conditions are specified. Express the equations in terms of known parameters, leaving only Yi naught as the unknown quantity. Briefly describe how the equations will be solved and what quantities must be specified. So it's a long question, but kind of going off of part B, you just have to realize that the adiabatic temperature conversion are the conditions at which the reaction in an adiabatic reactor stops to equilibrium. So again, where this energy balance line meets the equilibrium curve. So basically all that means is that your energy balance conversion has to be equal to your equilibrium conversion. And you can rewrite your energy balance to now include species, the inert species. Now from here, you just rearrange your energy balance to solve for your x. So you get XCB is equal to CPA plus I.
Why are the CPs different signs?
I think that's supposed to be positive. I think that was just a.
And the negative is supposed to be the outside.
Yeah, and then I is just the species of the inert species. So this is your energy balance equilibrium. Now you want to solve a equation for equilibrium conversion, which I'll do over here. So you can start from the top 10. ACT is going to be equal to CBCC, CA.
Hey, shouldn't the calculation the denominator be positive?
There should be a negative outside of the CPs.
Okay.
No.
Not bad.
Up top.
0 equals negative.
Oh, my bad.
And then the bottom equation is right because when you move over the delta H reaction, it's in a denominator.
Yeah.
Just
Okay. Yeah, that makes sense. Yeah. All right. So let's go through and simplify this again. ACT is going to be equal to F naught x squared over F naught 1 minus x times pi dimensional flow rate.
Did we still have temperature time?
Do you still have what?
Temperature time? Oh, well, we got to take it off.
Yeah. Yeah, it's coming right now. So you can recognize F naught over V naught again is just concentration. That's C naught x squared over 1 minus x 1 plus epsilon x.
Why is the FA not squared on this section?
Because I just took out this one. So it's squared over 1. So this equals KCT. Rearrange now. So you can get KC XT C naught T naught. And you can factor the bottom. And you can bring all of this to the other side. So the end goal is to get everything in terms of just x equilibrium in terms of everything else. So erase this. So you can bring that over, you get 1 plus epsilon x. Times KC. Then you can divide all this by x squared, so you can either go through and, or subtract x squared from all that, so kind of keep everything separate and do it like this, or you can just use a calculator, solve function if you have a T at 89. So what you end up getting is ACT over C naught, T naught, plus epsilon minus 1, KC T. Epsilon KC T C naught. Plus 1 times x squared equals 0. And then from here, final form will be equilibrium conversion is going to be, if you say this is, let's call that gamma, this beta, and all this alpha. then you get this for equilibrium conversion. Your energy balance conversion was pretty simple, so then, but I just erased it, so I'm just rewrite it real quick. So then now that you have these two equations, you just have to list out what you do. So what you do is you just set the equilibrium conversion to the energy balance conversion. That'll give you Y I naught. And things you need to specify are your operating temperature, your initial temperature, your initial concentration, heat capacity of species A, heat capacity of the parent species, your heat of reaction, and then your equilibrium constant. So after you solve for this equation and x of the energy balance, all I have to do is say that you set them equal to each other to get Y I naught, and then specify those.
How does setting